Okay, the second review, we're still on the same page, 533. These are improper integrals. So the first batch was covering 81, 82, 83, 84, and 85. And the last batch will cover also 81, 82, 83, 84, and 85. Here, we're doing the improper, that's like 8.8. So I notice that this function has an issue at 0 because the integral is running from 0 to 1, but this is not continuous at 0. So I'm going to integrate first like I did before, and I'm going to tackle this like we did that section. I'll deal with the limits once I'm done with the integral. So I see a natural log. I let u equal natural log of x. du is 1 over x dx. We have a problem, which means its parts. dv will equal dx. And if you integrate, v will equal x. This is going to be u times v minus the integral of v du. If you multiply those two, you simply get dx. So this is x natural log of x minus x evaluated. Now I'm going to bring in the limit. I'm going to say from t to 1, and I'm going to take the limit as t approaches 0. And in this case, do you see you can only approach 0 from the right? And this is going to be the limit as t approaches 0 from the right of 1 natural log of 1 minus 1, that's a 0, minus t natural log of t minus t. And here, I'm trying to figure out how this works. This is going to be a negative 1. And I'm taking the limit as t approaches 0 from the right of negative t natural log of t plus t. And here I do notice that I am getting this is 0, that's not a problem. But here I'm getting 0 times infinity. I need to manipulate the problem, and I know how that works. We never touch a log, as we mentioned. So I take the limit as t approaches 0 from the right of negative natural log of t over 1 over t. And now this is infinity over infinity. And by L'Hopital, every time you use L'Hopital, you put the h right there telling me that you used L'Hopital, so I know what you're doing. And this will be 1 over t and negative 1 over t squared. And I'm going to take a bit more space. You see, I'm debating if I should move that to the right. And just, Okay, I'm going to rearrange those, so I move that up there so I can see it better. And that be a negative 1 plus the limit as t approaches 0 from the right. That's positive, and that's going to be really t squared over t, which is negative 1 plus the limit as t approaches 0 from the right of t, and that's a 0. So I'm going to get a negative 1, which indicates that this series converge. Next problem up, again, I noticed that this integral is really running this from negative 2 to 0. But we have an issue with negative 1, and negative 1 is in that interval. So what we're going to do, we're going to split this integral up. That's going to be the integral from negative 2 to negative 1. Plus the integral from negative 1 to 0. And this is nothing more than theta plus 1 to the negative 3/5. So we integrate one part, and if that diverge, we're done. This is going to be really add 1 to the power, that's theta plus 1. If you add 1 to the power, that is 2/5. Divide by that, that's 5/2. Evaluated from negative 2 to t, taking the limit as t approaches negative 1, negative 1, and in the first part, you're approaching that from the left. Alright, and that turns out to be the limit as t approaches -1 from the left of 5/2 into fifth root of t plus 1 squared minus fifth root of -2 plus 1 squared. If you put a -1 in there, that's a 0. So that's -5/2 minus a -1 plus 1. Okay, that's finite, which means we need to integrate the second piece. Here we're going to take the same deal. This is going to be 5/2 times theta plus 1 to the 2/5. That's not going to change. Evaluate it from t to 0. And we're going to take the limit as t approaches -1, in this case from the right, and it's not going to make much of a difference. That's going to be the limit as t approaches -1 from the right of 5/2 times, if I put a 0 in there, 1 to the 2/5 minus t plus 1 to the 2/5, and when I put -1 in there, that's also a 0, and that's going to give me an actual 5/2. So that equals a -1, therefore it converged. That's all that matters to us. Does this converge or diverge? I gotta do a better job on the rest. So I'm gonna do one at a time actually. I'm not gonna put two side by side so that I have plenty of space. Here I look at this problem and I notice that this requires partial fractions. So if I take 3v minus 1 divided by factor of v squared out, that would be 4v minus 1, right? That is a over v plus b over v squared plus c over 4v minus 1. Clear the fractions. Okay. Clear the fractions. 3v minus 1 equals av into 4v minus 1 plus b into 4v minus 1 plus cv squared, and let v equal 0. If I let v equal 0, I'm going to get a -1 equal. That's a 0. A 0 in there, that will be b times -1, and a 0 in there, that will be a 0, which means b is 1. And if I let v equal 1/4, so I'm going to get 3/4 minus 1 equal a 1/4 there, that will make this a 0, a 1/4 there, that will make that a 0, and a 1/4 there will make that 1 over 16. So if I clear the fractions, this is times 4, that's a 12, times 16, that's a 16, equal c, right? And c will equal a -4. I got c. So if I know that this is a -4 and this is a 1, I could just choose any value instead of using systems of equations. If I let v equal, let's say 1, I'll get 2 equaling a 1 for v, that will make that a times 1 times 3, a 1 in there, b is already 1, that will make that a 3 minus 4, and a 1 squared is 1, and I could solve for a. 2 equal 3a minus 1, so that will be 3, that means a is 1. So here I got this to be the integral of 1 over v plus 1 over v squared minus 4, and here over 4v minus 1 dv. That will be natural log of v plus minus, let me see, that's v to the -2, add 1 to the power, divide by that, minus 1 over v. And this will be minus natural log of 4v minus 1, and you're going to divide by that 4. And now I'm going to evaluate this from 1, let me see, 1 is fine, yeah, this is not continuous. At 0, we have a problem, and at 1/4, we have a problem. So we're starting from 1, so that doesn't matter. So 1 to t, and we're going to take the limit as t approaches infinity. We always have to check. So that is the limit as t approaches infinity of natural log of t minus 1 over t minus natural log of 4t minus 1 minus, if you put the 1 in, natural log of 1 minus natural log of 3, that's a 0. That doesn't matter right there, that's a constant. I'm going to continue this problem. Actually, this is what I was thinking. I could take all of this work and move it to the right. That's why I chose to do a problem at a time, to make sure that we don't squish things anymore. So those I'm going to shrink just a bit. Oh, come on. Okay, somehow it's not registering. There, technology. Shrink it a bit, and I'm going to shift that to the right. There we go. And now I could say that is a 0. That's not a problem. But here I'm getting infinity minus infinity, right? This is here. This is just 1 plus natural log of 3. That's not going to change the outcome. So if I combine those two logs into one, that's the limit as t approaches infinity of natural log of t over 4t minus 1 plus 1 plus natural log of 3. And this will be natural log of the limit as t approaches infinity. If I divide by the highest power term of the denominator, that's 1 over 4 minus 1 over t. That's a nice trick. Instead of L'Hopital, you could do that. That will approach 0. I would be left with natural log, and this limit will give a 1/4 plus 1 plus natural log of 3, which is a finite answer. And therefore, this series converge. This integral converge. Next problem up, I want to look at number 60, and I noticed that this requires integration by parts once. This only has an issue with negative infinity. So if I let u equal x, du will be dx, and if I let dv equal e to the 3x dx, and if I integrate, v would be e to the 3x divided by 3. So that makes this u times v x e to the 3x over 3 minus the integral of v du, that's 1/3 e to the 3x dx. That becomes x over 3 e to the 3x minus 1/3 e to the 3x over 3. And now I'm going to evaluate that from t to 0, and I'm going to add the limit. You could do that. T approaches negative infinity, and let's see what happens here. This would become the limit as t approaches negative infinity, and if I take this as x over 3 e to the 3x minus, you substitute the 0 in first, you will get 0 minus 1/9 minus t over 3 e to the 3t minus 1/9 e to the 3t. Now, the negative 1/9 we really don't worry much about, that's not a big deal, plus the limit as t approaches negative infinity of negative t over 3 e to the 3t, plus I could have factored a 1/9 out, but I don't want to make this messier than it is. As t approaches negative infinity, I know that approaches 0. So this is the only piece that's left. That is infinity times 0. So the negative 1/9 I'm going to leave alone, and I'm going to work with this. I'm going to write this as the limit as t approaches negative infinity. And I'm going to say that's negative t over 3 e to the negative 3t. Now that is approaching infinity. Negative times negative is a positive. And as this is negative, that's going to be infinity. I could say by L'Hopital, the negative 1/9 is not part of this. That is the limit as t approaches negative infinity of negative 1 over, that will be negative 9 e to the negative 3t. As t approaches negative infinity, if you don't see it, you could move this up, right? That's going to grow up, and that's going to approach a 0. And therefore, I'm left with negative 1/9, and therefore, this series converge. (62) is the next problem up, and we already know what that is. If I want to integrate that, that would be 4 times. We said we're going to memorize 3 integrals. That's one of them. That will be 1 over 4, the inverse tangent of x over 4. If you recall, those cancel out, right? So I'm left with the inverse tangent of x over 4. And this I'm going to split into 2 parts, right? I just integrate it. I'm going to really work this out, this integral. Oh, come on. Okay. Lost track. Here we go. I just want to move this out of the way first. Okay. Here we go. I'm going to write this as the integral from negative infinity to 0 of 4 over x squared plus 16 dx plus the integral from 0 to infinity of 4 over x squared plus 16 dx. So this is actually going to be the inverse tangent of x over 4 evaluated from t to 0, taking the limit as t approaches negative infinity plus the limit as t approaches infinity of inverse tangent of x over 4 evaluated from 0 to, let's say, b. Change that so that you wouldn't mix those up. Those are two separate. Those are two separate integrals. And this is going to be the limit as t approaches negative infinity. Inverse tangent of 0 is 0 minus inverse tangent of t over 4. And we know the graph of a tangent. I went over that with you and I told you you're responsible for that graph. Inverse tangent is a graph that maxes at pi over 2 and minimizes at negative pi over 2. So this is 0. This will approach pi over 2. That will be 0 minus pi over 2. I'm sorry, negative pi over 2 because you're approaching negative infinity. So this gives me pi over 2. Now when I get to this piece, that is plus the limit as b approaches infinity, the inverse tangent of b over 4 minus the inverse tangent of 0, well that's 0 as well, and as t approaches infinity, that will approach pi over 2. So this limit will be pi, therefore it will converge. And the work for the integral is right there. That doesn't look very pretty, but we get the point. And the last problem I wanted to tackle here was this problem. I know you don't like that integral, but you should get used to it. We're going to do integration by parts twice. Hopefully you remember that. U let u equal, I'm going to choose the cosine of u. Du is negative the sine of u du. dv is e to the negative u du. And if I integrate, I'll get v to be negative e to the negative u. U times v, negative e to the negative u cosine of u, minus the integral of v du. So negative times a negative, that makes that e to the negative u sine of u du. That's going to equal negative e to the negative u cosine of u, minus, now, if I really take this integral and I do integration by parts again, let u equal the sine of u, du will be the cosine of u du, dv would be whatever's left over, which is e to the negative u du, and if I integrate, I'll get v to be negative e to the negative u. So this integral has a minus in front of it, u times v minus e to the negative u sine of u, minus the integral of, and that becomes a plus e to the negative u cosine of u du. So if I read the far left, that's the integral from 0 to infinity. Well, let me not worry about 0 to infinity yet, like we agreed. This is the integral of e to the negative u cosine of u du. If I skip the middle part, if I skip this part and get to this equal right there, copy that down, that's negative e to the negative u cosine of u plus e to the negative u sine of u minus the integral of e to the negative u cosine of u du. And we knew this was going to happen. We knew you were going to get it back and you're going to do an equation by parts twice. You could use the shortcut like I showed you in class. Move this to the left and that becomes twice the integral of e to the negative u cosine of u du equaling e to the negative u times the sine of u minus the cosine of u. And if you really want to divide by 2, make that 1/2, and there it is. So all of this work is to integrate. We didn't take the limit yet. 1/2 e to the negative u sine of u minus the cosine of u. And now we're going to look at the limits. We're really going to take, so this is now a new problem. Zero to infinity. I'm going to evaluate that from 0 to t and take the limit as t approaches infinity. So this problem on its own now, let me see, I could probably make it right there. That's the limit as t approaches infinity of 1/2 e to the negative t times the sine of t minus the cosine of t minus, if you put a 0 in, you will get 1/2. E to the 0 is 1. Sine of 0 is 0 minus 1. So that's a constant. That last part is simply 1/2. And now I'm dealing with this limit. And how am I going to figure this out? Well, that's the limit as t approaches infinity of 1/2 sine of t minus the cosine of t divided by e to the t. As t approaches infinity, this will approach infinity and those will isolate. At most there'll be a 2 and lowest will be a negative 2. So since that's a number that's growing back and forth, that's going to approach 0. And I'm left with 0 plus 1/2, which is 1/2. Of course, if I wanted, I could have split this up and did those individually, right? And there's your homework for this batch. This is homework number 2. You're gonna go to page 533 and do number 63 through 67 odd.